This is AP Physics Derivations Review. I kind of broke it down into mechanics and then electricity and magnetism. We've already done a lot on the electricity and magnetism, so I'm going to focus a little bit more on the mechanics. Here I have basically some of the key ideas, relationships that lead to more derivation-based problems. Newton's second law, net force equals mass times acceleration. Got a situation where you've got forces, free body diagram, substitute variables in, and you can solve down for whatever you need to. Likewise with the rotational form, net torque equals I alpha. Substitute in your I equation. Sometimes you'll end up substituting in A is equal to R times alpha, using that to substitute for alpha. And then the torque, R cross F. And that depends on the situation. Variables, and then solve for what you need to solve for. With Newton's second law, oftentimes if you're asked to set up a differential equation, Newton's second law is oftentimes a place you will start, and you will do a substitution of A equals dv dt, or down here on the bottom, alpha is equal to d omega dt. Once you substitute those into the respective equations with whatever goes in on the other side for net force or net torque, you have a differential equation. Oftentimes AP will ask you to set up a differential equation in one part and then solve in another part. But that's one way you get to a differential equation. Drag force. Drag force generally we modeled as force being proportional to the velocity, but in the opposite direction. We're going to talk through a derivation with that in just a second. And then center of mass and moment of inertia, which mathematically are very similar equations. Center of mass has an integral of x dm. Moment of inertia has an integral of r squared dm. So there's a difference in a power and a significant difference in terms of the interpretation of what you get. And we'll talk through derivations with those here in just a second also. So, drag force. I set up and solved down a drag force derivation here for basically an object that is falling, where that drag force is equal to negative b times v, or that drag force is proportional to the negative velocity, and we want to derive an equation for v of t. So we start with Newton's second law, net force equals mass times acceleration. From your free body diagram over here on the side, bv would be the drag force upward, mg downward. I did, in this case, make the downward direction positive. So mg is positive, and then my acceleration, which would be downward also, goes in as a positive. So mg minus bv equals m times a. Then we substitute in the next line dv dt, like we talked about a second ago. Differential equation. And sometimes it's just recognizing that that's the kind of thing that they're asking for a differential equation. Now, from there to be able to solve down, we need to get all of the v terms to one side and everything else to the other side. So I've done a couple of steps of algebra there to be able to deduce down to 1 over m dt, and then 1 over mg minus bv dv. We're going to integrate both sides. To be able to integrate, we're going to use u substitution and let u equal the mv minus bv. Then du dv will be a negative b, and then we can solve down for dv. Doing those substitutions, and actually I integrated on the left side because it was a pretty simple integration from 0 to t. Guess I should put my endpoints here. 0 to t on that side. For dropping an object here, this goes from 0 to v. And so then on the right side, doing the substitutions, we get the integral of u to the negative first power du over negative b. I threw the negative b over to the other side of the equation and integrated to get the natural log of u, put back in the mg minus bv, plugged in my endpoints of integration, and then the rest is basically algebra to be able to solve for your v of t equation. So the derivation of this is very, very similar to the math we did in the deriving of the RC circuits, and then also the RL circuits. In terms of graphs, your ideal graph, acceleration constant, negative 9.8. That means the velocity graph is a diagonal with a slope of negative 9.8, and your y of t graph is a parabolic curve. When you have air resistance with the drag force proportional to the negative velocity, then your acceleration doesn't stay constant anymore. The faster the object goes, the greater the drag force. The greater the drag force, the lower the net force, the lower the acceleration. And so then your drag force, or your acceleration, approaches zero as we move across our line here. That means our velocity increases rapidly at the beginning, but approaches a constant value, and that's the coefficient in the equation, mg over b, and we would term that the terminal velocity. And then your y versus t graph, if you're approaching a constant velocity, you're approaching a constant slope. So you start with a curve, changing velocity, and then, as best I could on the graph, showed that approaching a straight line. So that's your basic idea of a drag force and the derivation that goes with it. Center of mass on the left side, moment of inertia on the right side. I did not do complex derivations on these because I wanted to walk you through the logic. Now that we've done so much with charges in second semester, these should make a lot more sense. So then on each of them, I have a uniform rod of mass m and length L. I've taken the equation, which in each case has a dm, and I've identified a dm on the rod, and then the location of that dm, which for the center of mass we use the variable x. So then the thickness of that dm chunk would be a dx, and then for the moment of inertia, r is the variable, so then the thickness of that chunk would be a dr. On both ends we did mathematical substitutions with linear mass density, mass over length, or dm over dx or dr, solved down for dm, plugged it into the base equation, pulled out the constants, and then integrated, summing from one end of the rod to the other end of the rod for those dx or dr chunks, and arrived at the final equation: center of mass, point at which the object balances, uniform rod, it's in the center, moment of inertia, 1/3 ml squared. Now, if your rod is not uniform, then typically what you're going to have is some type of equation that describes that mass density. And so you would have maybe a lambda of r equation. And so then in that case, when you use lambda, you would skip the mass over length and go to a dm over a, I'm going to flip my variable to a dr because I wrote that above, dr, and then dm would be lambda dr. And then you can do a substitution. You can integrate both sides to arrive at the total mass. From there, it really depends on what you have. But that lambda of r equation would go right in there if you are doing that integration. And then the logic on the other side on moment of inertia is exactly the same. Now, on electricity, not magnetism, just electricity this year, your base equations that you use for derivations are Coulombs law and Gauss's law, and those are both pondering electric fields, and then Kirchhoff's loop rule, which applies generally to circuits and then also specifically to RC circuits. So, Coulombs law and Gauss's law, we've gone into pretty much detail in the last 3 weeks as we've been reviewing on those, and we've done some derivations with both of those. So if you have questions on those, let me know. Kirchhoff's rule, remember that is dealing with the voltage. In terms of the derivation, loop rule is oftentimes what we use, and that's basically the total voltage, the sum of the voltages around any closed loop is going to equal 0. So then if you have resistors in your loop, V is equal to I times R. If you have capacitors in your loop, base equation C equals Q over V. So then V would be a Q over C. So then depending on what the elements are, you're substituting in one of those. Batteries, you have the voltage or the EMF that is given there. Set up the equation, and then it depends, like in an RC circuit, what is changing. In that case, the current is changing. So then we set up a dq dt for I and solve down. I have another video that I did for you earlier in the year that walked through the derivations for RC circuits. And instead of me redoing that here, I'm going to paste that link also so you can review those derivations. So that gives you kind of an overview on derivations. Ponder physics.